My name is Adelbert Chang. I'm a lead data engineer at Target, so I'm an industry person. I also am a member of Type Level, which is sort of like a community or umbrella project of a bunch of open source functional programming libraries. And I help maintain the CATS project, which is a general functional programming library, and Frameless, which is intended to be sort of a type-safe wrapper around Spark. But today I want to talk to you guys about type classes, specifically what they are, how we encode them in Scala, the limitations of the encoding, and sort of what we can do moving forward. So to give a quick introduction to type classes, they were introduced in Haskell and are in general a way of providing a form of ad hoc polymorphism. Generally, when we think ad hoc polymorphism, we think function overloading, so doing something like writing a bunch of functions with the same name but across different types, so that when you call the function with a value, the compiler will figure out which one you meant, and just sort of gives the behavior that the function can do different things depending on what the input types are. Type classes provide a different spin on this by introducing the notion of the type class and an instance of the type class. So instead of writing a bunch of different functions with the same name but different input types, you write one function that takes in a generic type, and you constrain that generic type to have an instance of that type class. So something that's sort of type classy would be like a Java comparator object. So one key difference here is instead of having the behavior encoded along with the data type, so like you would have in subtype polymorphism, the comparator object encodes behavior separate from the data type. And so functions that use this would take in two parameters of, say, type t, along with a comparator object that's comparator t. So it takes in the instance along with the argument. One difference between type classes and this approach of explicitly taking into instance is instance resolution happens automatically. When you go to call the function, the compiler will go and figure out behind the scenes to make sure the correct instances are defined. So this is sort of like how implicit resolution works in Scala. And this turned out to be very useful because we no longer have to worry about like explicitly passing in the instance object, and the instances can be defined sort of in a complex way. Like you have an instance of this type class only if some subcomponent of your type has an instance of another type class. So the fact that the compiler handles all this plugging for you is very useful. And in general, type classes end up being a very natural tool, a very nice tool for specifying a lot of like the mathematical, category theoretic abstractions that a lot of modern functional programming likes to leverage. So for these same reasons, a lot of Scala programmers have wanted something like type classes in Scala because Scala allows us to do the kinds of modern functional programming that people are interested in, and type classes are a very good tool for that. And as it turned out, Scala, while it doesn't have an explicit notion of type classes in the system, it has enough features there to sort of emulate them to an extent. And so the way this generally works is we use traits for type classes, and I'll show an example in a bit. But so type classes are more or less an interface, and so we'll use traits for describing that interface, like you would usually for, say, OO subtyping. We use implicits for defining instances, and then we use implicit arguments for constraining functions. So this is where the automatic lookup happens. And then we use subtyping for specifying relationships between type classes. So just like in sort of object-oriented hierarchies, you can have a very general type class and then maybe a type class that encodes equality. And then you can have something more specific, like a type class that encodes ordering. And so we use subtyping for specifying those relationships. And this approach has been working for the most part for a good number of years. So we have a lot of open source libraries that across a variety of domains that people use, and they use type classes as sort of the main abstraction mechanism. So we have libraries like Scala and CATS, which are just general functional programming libraries. We have libraries like Scodec, Argonaut, Circe, which are libraries for talking about binary serialization and JSON serialization. Algebra talk about numerical computing, so things like rings, modules, vector spaces, matrices, and then FS2 is for streaming. So type classes aren't just like a very niche tool, they end up being a very natural and nice tool for talking about a variety of domains. So an example of a type class in Scala, this is just how we would define a type class. In this case, we have something called functor, which talks about type constructors, which support this map operation. We can define instances of this type class by just declaring an implicit value of the appropriate type. So in this case, I want to implement functor for list, because list can support a map operation. So I declare implicit value for functor list, and then I will stick it in some object somewhere. And then we can also write our actual quote, overloaded function. So we define void that takes in some generic type f of a, And you can call void as long as the f that it infers has a functor instance. And so notice one nice property we have here is that instead of taking in the functor instance explicitly, it just asks for the information it really cares about. And then so when you call it, it'll automatically verify for you that the type of the value that you're passing in is okay. So if we call void of, say, list 1, 2, 3, it will check to make sure that we have a functor of a list, which it will see, and it will happily go through. And if we try to call void for, say, set, it'll notice the instance is not there, and it will fail. And so you can see that in the implementation of void, we sort of leverage the functor f specific implementation, which gives us the sort of type-directed behavior change that we saw before. We also want to be able to talk about more specific type classes, right? So we can talk about the monad type class, which abstracts over type constructors that support this flat map and pure operation. And as it turns out, if you can implement flat map and pure, we can implement the aforementioned map method, which suggests that monad is strictly more information than functor. And so just like with regular subtyping, we'll say every monad is a functor. And so this means that if I can implement monad for some data type I have, say list, then I just have to implement flat map and pure, and then I get map for free, and any context that expect a functor will be happy with it. So one really important property we want from this is if we're working in a context where we know we have a monad instance, then we will also want to be able to sort of transfer ourselves in contexts that only require a functor instance. So in the body of need monad, we know that f has a monad instance, and then maybe we want to call void along the way. And so when we call void, void is going to make sure that the f that we've given it has a functor instance. And this works because it knows that we have monad, and monad is a subtype of functor. So through the usual subtyping rules, this is fine. We soon run into problems, though. So consider what happens when we have, say, another type class called traverse. What it actually does isn't really important. What's important is that traverse also is also a subtype of functor. So as long as you can implement this traverse method, you can get a functor for free, just like with monad. And we want to write a function parametric over some type constructor that's both a monad and traverse. And along the implementation of the function, maybe we want to call void as before. And we might expect this to succeed because it succeeded in a previous example. Void's going to ask for a functor. We still have monad as before, and so we expect this to type check. It turns out this doesn't work because we now have this additional traverse constraint. And when void goes to look for a functor in the context, it'll get one through monad like before, but it also now has a valid one through traverse. And it doesn't know, in the system of implicits, it doesn't know that these two are compatible or equivalent in some sense. So instead of picking one arbitrarily, it's going to just throw up and just say, I don't know which one to pick, ambiguous implicits error. In this particular case, we can fix the problem by just explicitly passing in the implicit argument, which basically takes the implicit resolver out of the picture, and we tell it explicitly which instances we want. This can get more complicated as we add more type classes and more complex type class hierarchies. This also breaks the situation where a lot of these libraries that provide type classes will also provide syntax enrichments through like implicit classes. So you can imagine if we have some value of type f of a, we want to be able to add a map method onto it, so long as f has a functor instance. And we do this through implicit classes. But if we're in a context where we have ambiguous functor, then we no longer can trigger that implicit class, which means we lose the syntax. And moreover, this specific problem can no longer be solved by explicitly passing in an argument. So what I'm arguing is that this sort of subtyped implicits encoding of type classes has been working for the most part for the past couple of years, but can fail whenever the type class hierarchy branches. And this has become more relevant recently, especially in the sort of, I guess, open source community, where there's been a lot of interest in sort of these effect tracking systems, which end up using a lot of functions that are parameterized over branching type class hierarchies. So just to give you guys an idea, this is the type class hierarchy for cats. So cats has been in work in progress for 3 or 4 years, and one of the main goals we had was to try to come up with a very minimal core of type classes that we want people to be able to use. And 3 or 4 years later, this is what we ended up with, because we found out that even for like really like non-super complex programs, a lot of these like fine-grained type classes ended up being very useful, and so our type class hierarchy actually branches a lot. And so if like one response might be like, okay, we never really deal with branching type class hierarchies, the response to that would be, well, it's sort of unreasonable to restrict ourselves to sort of a linear chain of type classes. We want to be able to talk about branching type class hierarchies, and our encoding of type classes should be able to talk about something as simple as this. So what can we do? Earlier I mentioned that type classes come from, or sort of inspired by Haskell. So we can see what Haskell does to solve this problem. So Haskell does have first-class type classes. And one very important property they have is this notion of coherency. So coherency in general talks about the property that every type class or every different valid typing derivation for your program should result in a program with the same dynamic semantics. In the context of type classes, this means that no matter what instances I end up picking, if I change the type class resolution algorithm, I should not be able to observe it from running the program. I should get the exact same program. And the way Haskell achieves this specifically is through a syntactic method. Basically, they restrict when and how you can define type classes, and this ends up having a property that across the entire Haskell ecosystem, you have a globally unique instance, which means for a particular type class type pair, there's only ever one instance in the entire world, which basically means like no matter how you resolve that type class instance, we know it's going to be the same because you only had one instance to resolve to anyways. So what this means in the earlier example of traverse and monad, it means so when we resolve functor, we know there's only ever going to be one functor instance in Haskell, which means that when the implicit resolver or the type class resolver goes to decide, should I go through traverse or should I go through monad, it doesn't really matter because we know we're going to end up at the same functor anyways. Whereas in a more general system of implicits, we don't have that property. Sort of a more complex example is consider a type class hierarchy that talks about equality and ordering. So let's say we know that we have the ability to order a list of A's. Starting from that, we can say if we can order a list of A's, I can just order just plain A's. And if we can order just A's, I can compare A's for equality. Starting back again from ordering lists of A's, if I can order a list of A's, I can compare lists of A's for equality. And if I can compare a list of A's for equality, I can compare just A's for equality. So we sort of have two different resolution paths, starting from ORD of list of A to equality of A. And we want to be able to know for sure that the equality of A we end up with is the same. This is a very important property to have because it allows us to sort of refactor our programs freely without having to worry about like, oh, I subtly changed how the flow of the program resolves the type class dictionary, and that subtly changes the semantics of my program. The way Haskell does it is sort of controversial because restricting the globally unique instance across an entire ecosystem is a pretty big restriction, and there's like proponents of, say, modularity, like especially like in the OCaml world where modules are a very important thing, don't like this, but implementation aside, the general notion of coherency I think is a very important one to have. I did mention earlier that open source community has been using type classes for a while, and it's been working more or less for the past couple years. So in the presence of this problem, what have we been doing? Basically, the solution has been, or the workaround has been, we've sort of just promised each other that we were going to declare just unique instances. And so when, as a library author, we have all socially agreed to like just define for a given type class type pair a single instance. And as a user of a library, we just sort of assume the library author has done their end. And this has worked for the most part, surprisingly. And generally, we also just like hope we never run into a situation where we have to abstract over two type classes that share the same superclass. But in the recent interest in sort of effect tracking in Scala and encoding various techniques have made this problem more and more prominent, which is sort of how I ran into this problem. So what are our options now in order to solve this? Because we're working in a general system of implicits, which has no notion of coherency. And Haskell's solution to this relies on coherency. So one option we have is to just sort of keep pretending like we have for the past 3 or 4 years and assume that we have type class coherency and just solve the problem of making the resolver pick one instance. So in the case of the traverse and monad example earlier, we just assume that the functor f through either of those is going to be semantically equivalent, and we just want to convince the implicit resolver to say just pick one of the paths. Another option we have is to actually fix the problem, to just go into the compiler and make the compiler type class aware. So I'll cover these two approaches really quick. So the first option is often referred to as a Scala encoding, at least in the open source community. And the reason we call it the Scala encoding was because this technique was proven out in a library called Scala by a guy called Adelbert Chang. And it identifies that the main problem with the subtyped implicits encoding is the subtype part. Because when the implicit resolver goes to figure out, goes to ask, I want a functor instance, it knows it can get it through either monad or traverse, both of which are subtypes of functor. At the same time, we want to be sure that we don't lose anything if we decide to say remove subtyping. And the key property that subtyping gives us is to be able to treat subclasses as superclasses, so sort of the usual subtyping benefits. And so what Scala does is turn around and says, what if we replace subtyping with implicit conversions? This still gets us the ability to treat subclasses as superclasses. The difference now being is with subtyping, it just sort of uses subtyping to coerce a monad into a functor. With implicit conversions, when you go to treat a monad as if it were a functor, it will trigger an actual function call in the background to convert it. But the difference now is implicit conversions can be prioritized in Scala, whereas with subtyping they can't be. So a sort of quick sketch of how the earlier type class hierarchy might look like in the Scala encoding is we'll define our type classes, but now for our subclasses, we won't have them extend functor. We'll just have functor as a member, and then we'll structure our sort of subtyped relationship with implicit conversions. So we'll have one that says that will convert a monad to a functor, and then we'll have one that will convert a traverse to a functor. And Scala implicit resolution rules will give priority to implicit conversions that are in subtypes, which means that in a context where we have traverse a monad and we want a functor, it's going to bias itself towards T2F, which is the traverse to functor conversion, because it's in a subtype. It's in a subtype relative to the trait that holds the monad to functor conversion. And then we define a library will presumably define a large hierarchy of type classes encoded in this way, and then at the top level we'll have like an object that extends the entire tree. And then on the client side, we'll just import that object so we get all the implicit conversions and everything sort of works as expected. So this works around the problem today. Potential problems with this is all these implicit conversions can incur like a performance cost. We don't really know what the implications of this are in, quote, real world usage. And compared to the subtyped implicits approach, this is a pretty heavy encoding, right? So like just with two type classes, we have to structure these implicit conversions very carefully to make sure we don't go back to hitting ambiguities. So this is more or less, this is the approach taken by Scala. So the project using this approach is Scala Z 8 now, and they're trying to effectively rewrite Scala Z 7 in this new encoding. And everyone's pretty much just waiting for Scala Z 8 to finish and see how it performs in the so-called real world. The second approach is to actually make Scala type class aware. And earlier this year, I had some time to kill, and so I just opened my laptop and banged on the keyboard for a couple of minutes and opened an issue against Dottie. So if you go to the Dottie GitHub repo right now, look in issues, you'll find this issue. And kind of surprisingly to me, I didn't realize that a lot of people would notice and like it. And then about a week or so later, I woke up to this issue being opened by Martin. And he had a proposal for a way of solving the problem, which is to have a way of allowing type classes to declare themselves coherent. So at a high level, what this looks like is we introduce a coherent marker trait that will change the behavior of the implicit resolver. And basically, when the implicit resolver sees something that has this marker trait, it'll just presumably just pick a path. One of the interesting things that fell out of this was we need to make sure that at runtime, the choice of the path cannot be detected. So one thing is, at the top level in Scala, we have like any, and any still has this Java object like equals and hash code, which can be used in a sort of evil way to be able to figure out like, oh, we chose a different path when we refactored our program. And so one of the proposed solutions is, can we introduce like a parametric any that has no methods on it, and so people can't disambiguate what path is taken. This is also still an open issue ticket, so I defer to that issue ticket for a more in-depth discussion. And one thing to note is the Scala encoding I talked about earlier works around a problem today. and it's going to be interesting to see how that fares in the real world. This approach solves a problem in a future Scala, and it's going to be certainly a nicer solution, I think, if we can get it to work, but it doesn't solve our problem today. And yeah, that's all I had for today. We have time for questions, if we have any. I think Paulo has a question.
So maybe this is silly, but if you have coherence, how can you declare the two instances, like let's say that a monad is a functor and that a traverse instance is also implies a functor instance and have coherence there? I mean, that seems, in both ones, seems hard to, how do you check that they are coherent without checking that the implementations are equivalent?
So the way Haskell does this is, so the problem is, so right now in Scala, when we implement monad, we just sort of get map for free. And similarly with traverse, we want to make sure those map things are equivalent. In Haskell, you don't get that map method for free. They make you define every single method explicitly. So that's the way Haskell does it. In Scala, what we're doing today is we basically just like hope that they're equivalent. I believe Martin's proposal for introducing a marker trait involves restricting under what situations you can have a marker trait be coherent, like in what situations can something be abstract, or when things must be final to ensure that like you can't have different semantics in a hierarchy. I'm not sure what the details are of his proposal, and I think even maybe he's not sure, because we're like last time I checked there was like a lot of debate around it. But I think he had, like the last time I checked, he had some sort of restrictions on what can be defined in order to try to enforce coherency.
Mm-hmm.
One question on the coherent trait. So can you give an idea where you actually put the coherent annotation or the marker trait? Is it on the superclass, on the functor, or on the individual subclasses?
It'll be on whatever like the root of the type class hierarchy will be. Okay. So so the idea being that you could have, so one contentious topic is, say for, I don't know, ordering for integers, right? One valid way is to order from least to greatest, another valid ordering is from greatest to least. Who's to say that least to greatest is like the one true instance, right? So the idea is I can define with this coherent marker trait, because it's just a marker trait, I can define like an ordering type class that's not coherent, so that would allow me to define two different instances. And then if I want to live in a world where it is coherent, I can also have like trait coherent ord extends ord with coherent or something like that. So it would be at the root type class. And generally for like, I think the quote cats and Scala Z folks have more or less settled on wanting to live in a coherent world. So maybe the standard library could provide non-coherent type classes, and then in the cats world we would just have one that's extends coherent and then work from there.
Perfect, thanks.
Hey, so I think definitely we should explore the coherent type classes approach in the compiler, and yeah, there's like 100 comments on that discussion thread, because it's not an easy thing to do. I think maybe one alternative approach, which I haven't seen much discussion on, is so basically with your example where you have something which is a monad and a traversable, the trouble comes because you ask the type system, okay, please give me an instance of monad and give me an instance of traversable, and then later on you want a functor, and then oops, you have two things, and then the type system doesn't know that they're the same for some definition of same. I think maybe we can solve the problem using even more subtyping instead of using less subtyping, and say implicitly ask, instead of asking for a monad and then asking for a traversable, asking for something which is both a monad and a traversable. So give me a monad T with traversable T. Mm-hmm. And then somehow magically the implicit resolver or some implicit rules can take an instance of monad, an instance of traversable, and come up with an instance of monad with traversable, so a subtype of both at the same time.
Yeah.
And then later on when you try to use a functor, then you don't have any issue because you only have one thing.
Yeah.
So I haven't really thought much about what this would imply or if this would solve all the problems,
Yeah.
but I think it might be interesting to look
Yeah,
at.
I think Miles Sabin had some. That was like the approach that he wanted to explore.
Mhm.
That's the approach he liked. I think that's definitely an interesting approach as
Yeah.
well.
So,
So it
yeah,
involved
I-
a change in the compiler, right? It's not something we could do today, I don't think.
I don't think so. Maybe with some like really clever implicit definitions to take a monad T and traversable T, return a monad traversable, whatever. But I think you need at some point to change the compiler because it's not going to be enough. I think it's easier probably in Dotty than in Scala C because in Scala C, intersections are not.
Like they're not
Yeah,
communicating.
they don't commute,
Yeah.
but in Dotty they do, so you don't have this issue.
Yeah.
Yeah, that's all. Thank you for the talk.
Thank you.
It seems like what you're getting when you do that example is sort of a diamond inheritance,
Yeah.
just sort of implicitly created.
Yep.
And you have the issue that a base class is being implemented in the two sides.
Yep.
And it seems like the usual solution is that at the diamond, at the base of the diamond, you have to define what,
Yep.
what map method to use.
Yep.
But when you do it implicitly, you don't have a chance to say that. But it seems like that's sort of the key thing that you need to be able to say.
Yeah, that's I guess probably the core problem. And Haskell's answer to that's basically ensure they're going to be the same, so we don't have to disambiguate.
Right.
So yeah, I think like with the diamond inheritance problem, like you solve it by like like you said in a subclass, you explicitly overwrite it, but because of the way type classes are used and the way it's resolved, you don't really.
You don't get a chance
Yeah,
to
you don't
write
get a
that,
chance to.
which is sort of the problem. Yeah. Okay.
So if you use inheritance to inherit the map method from say a monad and a traversable, the implementations of map may do different things, right?
Mm-hmm.
And so having coherent instances is not fixing that.
Are you talking about the marker trait thing or like what we're doing today? Or just
the concept of consistency, right? Even if instances are consistent, you're still gonna have to map in implementations that may do different things. Right?
Yeah. So I think that's where Paulo's or maybe it was his question. That was like, how do you ensure that? And I think Martin's idea was to just restrict have restrictions on what and where it can be defined. I don't know what the details of how he's going to do that are.
I haven't seen the discussion, so.
Yeah. So the issue ticket, there's like a 1,000 comments on like people arguing about what restrictions should be in place. But yeah, certainly we can, if we actually want to enforce a coherent world, we can no longer just allow people to just define their own
extensions.
map method. Yeah. And the way Haskell solves it is just like you define it once. You don't get it for free like we do in Scala.
Yeah. Mm-hmm.
Yeah. Thank you.